Welcome back to Maths with Mrs. J. We're now at the point where we're ready to learn some techniques on how to work out limits from the rule, from the function rule. As you've probably noticed according to the graphs, limits are quite easy to work out if the function is continuous at that point. If the function is just a normal run-of-the-mill garden variety function and it's continuous everywhere, no jumps, bumps, holes, gaps, whatever, then all you really need to do to calculate your limit is sub in the value where you're wanting to calculate that limit. So for example, we've just got a quadratic function here, just your normal run-of-the-mill quadratic function. If we want to know the limit of that function as x tends towards 2, all we need to do is sub in x equals 2. The good thing here is that the limit of a function is the function of the limits. We can just sub it straight in. We don't need to do too much here at all. And we just calculate that. We get what? 12 plus 10, which is 22, minus 9, which is 13. Perfectly fine. We know that the limit will exist there. It's a continuous smooth function. Limit from both sides will be the same. It will work. Even though this is a rational function and it will likely have some asymptotes and things going on there, if you were to sub in x equals 1 to this, there is no issue with it. We know that when x is 1, this function is perfectly valid. It is defined. So we can just sub in here as well, even though it's a rational expression. As long as the denominator is not 0, we're okay. So subbing in, we're going to get 6 minus 3 plus 10 all over negative 2 plus 7 plus 1, which of course is 13 over 6. And you can probably just leave it like that. You can change it to 2 and a 6th if you like. Now we're getting a little bit more interesting. Part A of this is not especially tricky, because notice that we're wanting the limit as x tends towards 6, and the sort of critical x value that we're talking about in this particular piecewise function is when x is negative 2. So when x is 6, things are certainly continuous by that stage. All we need to do is work out, well, which function is relevant to sub into. Well, if we're tending towards 6, clearly we're bigger than x equals negative 2. So what we would do here is we would sub in x equals 6 into this version of the formula. So we're going to get 1 minus 3 times 6, which of course is negative 17. At x equals negative 2, because that is a point where the function is changing, we need to really consider from above and below. So let's consider from above. So from above, the equals the limit as x tends towards negative 2 of this function here, 1 minus 3x. So it's 1 minus 3 times negative 2, which is 7. When we take the limit from below, then the rule that we need to use in that case is our other rule, because this is what happens when x is less than negative 2. So we're going to sub into x squared plus 5 here, and we're going to get negative 2 squared plus 5, which is 9. Now 7 and 9 are not the same number. The limit from the right and the limit from the left are not the same. So we say that the limit as x tends towards negative 2 of g of x does not exist, because those two one-sided limits are different. Okay, now we've got a situation, this is sort of like my type 2, where if you were to sub in, you would get 0 over 0. Now we know that we can't do that. These sorts of questions are quite common that you will need to be able to work with. They often come up particularly when you're doing derivatives from first principle. We're going to get something like that where we've got an h in the denominator and we've got a numerator that will also be 0 when we sub in h equals 0. And you might recall, if you've seen those videos about derivatives from first principles, what we do there is we factorise, take out a common factor, and then we can sub in. Now that might seem a little contradictory, but it's not. I'll just explain it to you. All right, if we're trying to do limit as x tends towards 2 of this expression here, it's pretty obvious if we try to sub in, we're going to get 0 over 0. So we can't go about it in that manner. However, both the numerator and denominator can be factorised. So let's do that. We're still going to write the limit because we haven't actually calculated the limit yet. So this will be x plus 6, x minus 2, and this of course is x times x minus 2. Okay, we're taking the limit as x tends towards 2. We're not saying x ever actually is 2. So it is okay to cancel those down because x is never actually going to be negative 2. Now to calculate this limit, we can say, okay, we can sub in x is negative 2. I can see why people get confused by that. It seems a little contradictory. However, I am not saying that x is ever going to be negative 2 for this function. It can't be. Function is not defined there. However, to calculate the limit in this indeterminate form, we can sub in. So we can now go 2 plus 6 divided by 2, which of course is 4. So that tells us what that function is tending towards as x is tending towards 2. Let's have a look at this one. To do this one, I'd be inclined to do a polynomial division to work out what the factor is going to be here. So let's just do that over here. We're going to be dividing by t minus 5. So we're going to get t squared, t cubed, minus 5t squared. We're going to get negative t squared. We've really got a 0t in there. Dividing through minus t, negative t squared plus 5t. So we get negative 5t plus 25, dividing through, and of course we get our negative 5. Of course it divides through, thankfully. So we've got our limit as t tends towards 5 of t minus 5 over t squared minus t minus 5 all over this. We know this numerator will factorise because if we sub in t as 5, it's 0. And thinking back to our factor theorem and our remainder theorem, well, the factor theorem is a special case of our remainder theorem. If you sub in t equals 5 to that polynomial and it equals 0, you know that t minus 5 is a factor. So we knew to expect that this will divide in. Now, because t is never going to actually be 5, we can now cancel, and now to calculate the limit we can sub in. So we're going to get 5 squared minus 5 minus 5, which is 15. Okay, all right. Let's just get rid of that. Okay, next one is something that might come up if you're doing a derivative from first principles, for example. Here, clearly, again, we're going to get 0 over 0 if we go ahead and sub in h equals 0 into that. That's not something we can deal with. So what we're going to do is try, if we can, to see if we can factorise. Now, before we can factorise, we're going to have to expand. So we're going to get 9 minus 6h plus h squared minus 18 all over your h, which of course is limit as h tends towards 0. The 18s will go, we'll end up with a negative 6h plus h squared or all over h. Now, you can, because h is not 0, you can divide through by h, and we get, well, we can show it as a common factor if we like. All right, and then we're going to sub in, so we get negative 6 plus 0, which is negative 6. This one here, factorising as such isn't going to be helpful. However, hopefully, if you've got your thinking cap on, you'll be thinking along the lines of conjugate. It is okay, when it's helpful, to multiply by the conjugate over the conjugate. So let's do that. It's perfectly valid to do that. So what we're going to end up with here then is the limit as t tends towards 4 of, in our numerator, we're going to end up with t squared minus your 3t plus 4. So minus 3t minus 4. And in our denominator, our 4 minus t, and then this bracket t plus square root 3t plus 4. Okay, numerator, when we factorise that, this would be t minus 4, t plus 1. Now, here's a little trick that hopefully you already know. If I want to cancel a t minus 4 with a 4 minus t, that will work. You'll get negative 1. T minus 4 is negative 4 minus t, so we're going to get a negative there. Now, if we try to sub in, it's actually okay. We're not going to get a 0 over a 0, so we're okay to now sub in t as 4. So we're going to end up with negative 5 over 4 plus square root of 3 times 4, which is 12, plus 4, which is 16. So that's square root of 16, which is 4. So we're going to end up with negative 5 on 8. So very, very useful little tip there. Okay, let's move on. Alrighty, so now we're talking about limits to infinity. With a limit to infinity, the leading term is the key thing that you need to look at. If you have a polynomial, basically it comes down to what your leading term is. If you're getting towards infinity or towards negative infinity, x to the 4th is going to be way bigger in magnitude than x cubed. All right, so we look at our leading power. We also remember that as x is tending towards infinity, anything like 7 over x or 7 over x cubed will also tend towards 0 because the denominator is getting increasingly large. The function itself will tend towards 0. Remember, your y equals 1 on x looks like that. As x is tending towards infinity, this function is tending towards 0. Let's have a look at these. This one clearly, the denominator is going to get increasingly large. 7 divided by an increasingly large number is going to get increasingly close to 0. This one here is going to be dominated by our leading term. If you're putting in a very large positive number and you're raising it to the power 4, you're still going to get an extremely large positive number. So this is going to tend towards infinity, positive infinity. If I had a negative there, it would tend towards negative infinity. All right, so it's the leading term that is the crucial part there. With ones like this, what we're going to do is we're going to divide everything through by the biggest power of x. So this is really, we can take it out as a common factor if you like. So we've really got 2 minus 1 on x squared plus 8 on x cubed over our x to the 4th, negative 5 plus 7 over x to the 4th. They, of course, cancel. We're nowhere near x equals 0 if we're tending towards infinity, so that's perfectly safe. Now, as x tends towards infinity, which of these bits is going to go towards towards 0, sorry? That will go towards 0, that will go towards 0, and so will that. So what we're going to be left with is 2 over negative 5. Let's do another one a little bit like that. What's going to happen here? We're going to divide everything through by t to the 4th. So we're going to get limit as x tends towards infinity of, if you like, take out t to the 4th, so 1 over t squared minus 5 over t cubed minus 9 over t to the 4th over your t to the 4th, 2 plus 7 on t. What's going to happen here is you're going to end up with 0 in your numerator and a non-zero number in your denominator. So what's going to happen is your limit will be 0 divided by 2, which is 0. If you get 0 over 0, you know you've done something funny and you'll need to use a little tip or trick to get out of the 0 over 0 situation. 0 over 2 is 0, okay? This one here, again, a little tip that you could probably use here would be, again, we're trying to be able to take out powers if we can. In order to take out the x squared out of your square root, you really need to first of all say, okay, well, under our square root, we have x squared times 3 plus 6 over x squared. And then in our denominator, we have negative 2x plus 5. We can take out our x now. Technically, it's an absolute value of x, but if you're tending towards infinity, of course, x is positive, so it will be the positive version. So we're going to be left with this. Now we can divide, oh, hang on just a minute. Let's just take out an x there, and we'll get negative 2 plus 5 over x. Cancel out our x's. Now when we do our limit, I'll show you what bits will go to 0. That will go to 0, and that will go to 0, because that's a 5 over x. So what we're actually left with is square root 3 over negative 2. Okay, that's another interesting one to have a look at. We've done the main sorts of ones that you need to be able to do as far as year 11 and 12 are concerned. I just want to show you a couple more just for interest. Having a look at this sort of situation, if you're tending towards a denominator of 0, what's going to happen is, if that denominator is coming in positive, so a tiny, tiny positive number, and you raise a positive number to an even exponent, obviously you're going to get an even number, and it will be extremely large if that number is extremely small. Even if your exponent is odd, if you've got a positive number, you're still going to be heading towards positive infinity. If you're coming from the left, however, coming in from beneath that point, you're going to have a slightly negative number, very tiny negative number. When you raise that to an even power, you'll be tending towards positive infinity. If n is an odd number, you'll actually be tending towards negative infinity, because remember, a negative raised to an odd power is a negative. Let's just look at these ones quickly. This one here, well, x is tending towards 0. This whole expression is going to be tending towards infinity. That's going to be positive regardless, so we're tending towards positive infinity. This one here, if we're looking at coming in from above of this expression, this bottom part will be a tiny positive number. Tiny positive number cubed will be a tiny positive number, but we've got a negative there dividing it. So this will actually tend towards negative infinity, because we've got our negative divided by a positive. If we're coming in from below, what we're going to get here is, this will be a very tiny negative number, and we're cubing it, so we'll get a very large negative number. Negative divided by a negative is going to give you a positive. That limit does not exist, because you're tending towards negative infinity from above and positive infinity from below. Last one, just two special limits I wanted you to know. You're not required to derive these, it's useful to know these bits of information. Let's use those bits of information, shall we? So obviously, limit as x tends towards 0, we can substitute in there. This bit here, sine of x on 4x is really, well, let's just rewrite this. This is really sine of x on x times a quarter, isn't it? So what we've got is this. Now when we sub in, we can just do each limit. We know that the limit as x tends towards 0 of sine x on x is 1. So this will be 1 times a quarter when you do the limit, plus 3 times, well, 0 squared, we're subbing in, and we're just going to get a quarter minus 2, which is negative 1 3/4. This one here, we know that the limit of 1 minus cos theta on theta as theta tends towards 0 is 0. What relationship is this to 1 minus cos theta? Let's have a bit of a look. This, using difference of two squares, is 1 minus cos theta, 1 plus cos theta. Okay, using your difference of two squares. We know that this limit is going to be 0. So when we work out our limits, we're going to get 0 times this limit. We're going to get 1 plus cos of, sorry, I'm swapping between thetas and x's here. I do apologise. We're going to get 1 plus cos of 0. What is cos of 0? Cos of 0 is 1. Still doesn't help you though, because you've still got 0 times 2, which is 0. So that limit will still be 0. All right, so there you have it. That's limits in a nutshell at sort of high school level. You will need to do a lot of practice. The main ways you will need to be able to calculate limits are if you are doing derivatives from first principles and if you are sketching graphs of rational functions. They're the main reasons why you would want to find a limit at high school level. Don't forget to subscribe to my YouTube channel if you like my videos.